Hello everybody, my name is Daniel Lager and I have the honor to give you a lecture on the thermal properties of energy storage materials in the frame of the STORIS project. So STORIS is an acronym for Storage Research Infrastructure Ecosystem and is focused on the research and development of the energy industry, searching for groundbreaking solutions for sustainable energy storage in Europe. In that presentation, we are focusing on the thermal properties of energy storage materials, and I will start with a short introduction about myself. I'm a research engineer at the Austrian Institute of Technology, and I'm working in the field of thermophysics and thermal analysis since 2007. And since 2019, I'm the head of the Associated Accredited Testing Laboratory at AIT. So my PhD degree I received from the TU Wien, the Vienna University of Technology, in 2017. And in my dissertation, I focused on the thermophysical characterization of thermal energy storage materials, especially on phase change materials and thermochemical materials. Prior to that, I did my diploma and my master's degree in electronics and biomedical engineering sciences at the University of Applied Sciences, Technikum Wien. And now, parallel to my work at AIT, I'm an external lecturer at the University of Applied Sciences, Burgenland. Let's start with an overview of my presentation. So I will start with an introduction to the AIT, the Austrian Institute of Technology, followed by some basics to energy storage systems and thermophysical properties. After that, we will come to the core of the presentation. This will be the different measurement methods and applications to determine the thermophysical properties of energy storage materials. The first method I will show in my presentation is the differential scanning calorimetry, DSC, and the application of the DSC on phase change materials. After that, we will have a look on the thermogravimetric and simultaneous thermal analysis, TGA and STA, and the method shown on thermochemical materials. The next 2 points will be about thermal transport properties. So light flash or laser flash, the technique to determine the thermal diffusivity, and the heat flow meter for direct thermal conductivity measurements on energy storage materials. Last but not least, we will conclude in the end. On this slide, you will see some terms and figures about the Austrian Institute of Technology. So the AIT belongs to two owners, the Federal Ministry of Climate Action, Environment, Energy, Mobility, Innovation and Technology, as well as the Federation of Austrian Industries. It is Austria's largest research and technology organization with approximately 1,500 employees. And it's divided into 7 centers with 4 subsidiary enterprises, with a total revenue of approximately 200 million euro. The focus of AIT is on applied research, on infrastructure systems, and on system competence. On this slide, you see the 7 centers at AIT and the 2 main subsidiaries, Seibersdorf Labor and Nuclear Engineering Seibersdorf. So the 7 centers are energy, health and bioresources, digital safety and security, vision automation and control, transport technologies, technology experience and innovation systems and policy. And the thermophysics lab is placed at the Center for Energy. Before we start with the core topic of this presentation, here you see a short overview about our lab capabilities and services. So we are measuring in a broad temperature range, starting at approximately -180 degrees centigrade up to 1,600 degrees centigrade. The main thermophysical parameters or properties like thermal conductivity, heat capacity, thermal expansion, thermal diffusivity, and density. But we're also looking on different characteristic temperatures, caloric effects, mass change and evolved gas analysis, and also other length change effects like shrinkage or swelling. So let's start with the interesting topic, energy storage systems. In that slide, you see some pictures about thermal energy storage systems as well as materials. So on the right side, for example, you see two electrical energy storage systems. Here we have pouch cell batteries, and here we have cylindric cell batteries. In the middle of the pic, you see here zeolite material, which is used for as a thermochemical material for sorption heat. Here you see a phase change material, a paraffin wax. And on the left side, you see a current project on cavern thermal energy storage. So this system is built in Finland, and this will be the world's largest cavern thermal energy storage with 1.1 million cubic meters of water and a capacity of 90 gigawatt hours. So this system is built at the moment from Vantaan Energy in Finland. Before we discuss the thermophysical properties of energy storage materials, I want to give you a phenomenological approach to these quantities. So let's take, for an example, a simple solid body. If you want to know how the temperature changes of the body, you would need a so-called enthalpy or specific heat capacity. The enthalpy of a substance increases with increasing temperature. So it can be described as an enthalpy change, which is defined by the product of the temperature difference and the heat capacity, Cp. The heat capacity of a material is specified through the substance type, the mass, and the temperature itself. If you want to know in which way and how fast the temperature change happens, then we are talking about the heat transport. So a heat transport between two places in a medium with different temperatures occurs through heat conduction, convection, or heat radiation. We are now talking about a solid body and we assume heat conduction. So heat conduction needs no transport of matter. Two adjacent particles transport heat through kinetic energy of the atoms or molecules due to the prevailing temperature gradient. Now we're talking about the so-called thermal conductivity, which is again depending on the place and the temperature. If you want to understand the change of the dimensions of your body, then we're talking about the thermal expansion. Because most substances increase their volume when they are heated at constant pressure. Some substances also contract during heating, as it can be seen for water below 4 degrees centigrade. This thermal expansion can be negative or positive and also anisotropic depending on the observed substance. The value here is called the thermal expansion or the coefficient of thermal expansion, and it's again depending on the place and the temperature. So now let's get back to energy storage materials and systems. In that case, we are talking now about thermal energy storage technologies. There are three different types on the market: the sensible thermal energy storage, the latent thermal energy storage, and the thermochemical energy storage. So as described before, with the specific heat capacity, the sensible thermal energy storage uses an enthalpy change due to the heat capacity and the temperature gradient of a material, the so-called sensible heat storage material. A latent thermal energy storage also uses the enthalpy change, but in that case for a transition of a material, so a transition enthalpy that can be a solid-solid transition or solid-liquid phase transition of a so-called phase change material. And last but not least, the thermochemical energy storage uses the enthalpy change due to a physical sorption or a chemical reaction of a thermochemical material. So for all of these technologies, you need to know the thermophysical properties of the storage materials to understand the storage capacities, the energy densities, as well as the thermal power on material scale. Now let's have a look on the sensible heat storage systems and the materials used there. So as shown before, we need to know the heat capacity and the temperature difference to determine the stored heat in the material or in the system. And there are some requirements regarding the material. So as you can imagine, you want to store a lot of heat in a small volume. So you want to have a high heat capacity, a high density, and you also want to have a high thermal conductivity, because the thermal conductivity gives you in the end the power, the charging and discharging power of your system. In this graph you see the stored heat of a material depending on temperature. So when you compare two materials with the same temperature difference, then you can store, for example here in the material 2, more heat with the defined mass and Cp value in comparison to the first one. And on the right side you see here a diagram which is showing different materials which are used for sensible heat storages. In the graph on the top you see the specific heat capacity value of these materials, and on the x-axis you see the thermal conductivity. So if you want to have a high specific heat capacity, you can see here, for example, water shows the highest value for the specific heat capacity in comparison to other organic fluids. When you look on metals, for example, they have a really low heat capacity. But the difference here is, for example, metals show a high thermal conductivity in comparison to water or to stones or minerals or other organic liquids. So that's the reason that one have to think about the material using for the application for the thermal energy storage, because depending on the application you want to have, for example, a higher Cp value, but you don't need fast charging or discharging cycles. But there will be also some applications where you want to have a high charging and discharging power, but you have enough space so that you can use, for example, materials with lower specific heat capacity. The graph here in the bottom shows more or less the same materials. The difference here is that on the y-axis you see here now the energy density related to volume, because here we have the specific heat capacity related to mass, and here it's related to volume. And the interesting thing is here, because of the high density of metals, you see that the energy density related to volume is pretty high for metals in comparison, for example, to water or other organic fluids. Okay, now we see the next system, the latent heat storage, which is based on phase transitions and phase transition enthalpies. In that case, we have some different requirements because you cannot change the phase change temperature of the material at all. So you need to know the actual phase change temperature of your material. Additional, you want to have a high phase change enthalpy, because this phase change enthalpy is defining your energy density. You also want to have low subcooling. What does this mean? For example, you have a material which has a solid liquid transition. Then you want to have this transition temperature from solid to liquid at the same temperature as the process from liquid to solid, so the crystallization should take place at the same temperature as the melting of your substance. And last but not least, you also want to have a high thermal conductivity. And when you now compare the graph you see here below, we have here again the heat, the stored heat, and the temperature on the y-axis. So when you are in the first phase of your material, you have more or less the specific heat capacity and the mass of the material defining the stored heat. But then you have the so-called phase transition enthalpy. And this phase transition enthalpy has now the effect that the temperature is not changing during the phase transition. That's the reason why we have here this line in parallel to the x-axis. And then when you, for example, in the phase 2, which can be a liquid phase, then you have another Cp for the liquid, and then the temperature is again raising and the quantity of heat is also raising. On the right side of this slide, you see again some clusters of different materials. Here you have on the y-axis the transition enthalpy, and on the x-axis now the temperature. And here's interesting to see, for example, when we look at phase transitions of salt hydrates or water or salt solutions, we're in the lower temperature range. When we go up here, then we see between 200 and 300 degrees centigrade we have the salts, and also again the first metal meltings, and at high temperatures here we have pure salts. In the graph below we see again the phase transition enthalpy, but related to the volume again versus the temperature, which is more or less the same picture than the picture above. Now we're coming to the third technology, the thermochemical heat storage, which is based on thermochemical materials. In that case, you use the reaction or the sorption enthalpy of the material with, for example, another gas phase. The material requirements here are a high enthalpy of reaction. You want to have fast reaction rates, a high thermal conductivity of the material, and also reversible and stable cycles, so that your material is stable during the whole storage, charging and discharging processes. In this diagram, you see the activation energy of a reaction over the time. So if you have a chemical reaction, for example, you want to have that your educt and your product have a different level of activation energy, because the difference of this activation energy defines the reaction enthalpy, and this reaction enthalpy is the enthalpy you use for the energy storage. On the right side you see here again a diagram where you have on the x-axis the temperature and on the y-axis the reaction enthalpy of defined reactions, here again related to mass and here again related to volume. Let's have a look on the diagram related to mass. So what you see here is that we are talking about megajoule per kilogram, so we have high energy densities. And interesting thing here is that, for example, sorption effects have more or less low reaction enthalpies in comparison, for example, to hydrate reactions or hydroxide reactions or ammonia reactions. But as you can see here, also the temperatures where these reactions take place are at different levels. Again, one has to think about, depending on the application, which kind of material class one is using for the application. Okay, now we come to the batteries, to the electrical energy storage systems. Also for these systems you need thermophysical properties. You need them for the battery cells and the components, for the housings and the packs, as well as for the cooling media, like cooling liquids. This is important to design and understand the thermal management for the battery, and also to understand thermal runaway situations of the battery cell. With this information, you can calculate then the heat flows during charging and discharging, for example, with a multiphysics tool, and you can optimize the thermal management and adapt also the safety measures for the battery cells. Now we discussed the reason why we need the thermophysical properties of these energy storage materials. Now let's come to the methodologies, how to measure them. The first method I want to show is the so-called differential scanning calorimetry. This calorimetry is used to identify the specific heat capacity of a material, as well as for reaction or transformation enthalpies. So this can be used, for example, for sensible heat storage materials, as well as for phase change or thermochemical materials. How does it work? So DSC, as it says, is a differential system. So what you do here, you measure a temperature difference between a sample and a reference. You see that here. And the sample and the reference are subjected to a controlled temperature program defined by this furnace. So when this furnace is heating up, you see that here, then the temperature of your reference and the temperature of your sample is changing. Let's assume that the reference and the sample is the same. Then the difference between these two will be zero. So there will be no DSC signal at all. It will be zero. But if you have some sample in the sample side and some nothing, for example, or an empty crucible here on the reference side, then you will see a temperature difference. And this is shown in this diagram. So you have here the temperature change of the furnace over the time. Then you have here in the blue dashed line the temperature change of the reference, which has a small delta T between the furnace and the reference. And now assume you have some sample which has a phase transition on the sample side. And here you see again a small delta T between the reference and the sample. And during the phase transition, the temperature is not changing until the phase transition is over. Then it's getting back into a increasing line, and also with a temperature difference to the reference. So with the DSC signal, you can calculate the specific heat capacity out of this delta T you measure between the sample and the reference. Here now an example for a DSC measurement of a phase change material. You see in this picture or in this slide two different heating rates applied on the same material. It's a paraffin wax with a transition temperature or a melting temperature at approximately 70 degrees centigrade. So when we compare the upper two diagrams with the lower two diagrams, in the upper two diagrams we have a low heating rate. So here we have a measurement of the apparent specific heat capacity from 50 to 80 degrees centigrade. And you see here that we have a small peak in comparison to the fast heating rate, where we have a lower peak but with a much broader peak base here with the higher heating rate. When we go into the detail, we also see that with the low heating rate we have here higher uncertainties of the CP value in comparison to the fast heating rate. So the asset and the drawback of the system shows that if you want to measure your phase change material with a high accuracy in temperature, you automatically get a low accuracy for the CP value, because the temperature difference between the sample side and the reference side is low, which means you have lower sensitivity and higher uncertainties for the specific heat capacity, but you will get a much sharper peak of your phase change, because the thermal conductivity of the material doesn't play any role when you have very low heating rates. There is the difference now when you heat up very fast. So if you heat up here with 10 kelvins per minute, you see that you have a much broader peak base in comparison to the lower heating rate, but you get much lower uncertainties of the specific heat capacity value before and after the phase transition, which means that for high heating rates it seems to be the better solution or the better methodology to measure the specific heat capacity of the solid and the liquid. But to understand the temperature behavior of the phase change, it is better to use lower heating rates. The next measurement system I want to show you is the TGA and STA, so the thermogravimetric analysis or simultaneous thermal analysis. What you do here is you measure the mass change of a substance while it's also again subjected to a controlled temperature program. So what is now the difference between TGA and STA? So the TGA describes only the mass change over the temperature, like you see it here. When you have some initial mass, for example, you want to investigate into a degradation process of a material, then you heat up the material until you reach a initial temperature, and then the degradation starts. So for example, some gas is evolving from the sample, and then you reach the final temperature where you reach the final mass, and you measure the change of mass versus the temperature. This would be a typical TGA measurement. So what is now the STA? The STA is now the combination. So you don't only measure the mass change of your sample, you also measure the heat flows of your sample. So you put a DSC sensor on the balance inside the system. So you get not only the mass change, you also get the heat flows during the measurement. What are the measured quantities? As I said before, mass change, and what you can also do, you can also measure reaction rates, because you measure also versus the time. So you see how fast your reaction occurs. And you can measure additionally with the STA system, so with a DSC sensor, the enthalpy changes of your material. Here I want to show you an application of the TGA-STA system with a sorption material. So we can measure the so-called sorption isotherms, and additionally the sorption enthalpy under defined gas conditions. And we can also understand or measure the time-related behavior, so we can determine the kinetics of these effects. In this example, we analyzed a zeolite 4A. You see it here. So it's also a molecular sieve, and here in this graphic you see the effect of adsorption and desorption. So if you have adsorption, in that case water vapor, so the water vapor is adsorbed on the substrate surface, so it's an exotherm event, so heat is released. And in the other way, if you want to desorb the water molecules, you have an endotherm effect, so heat is consumed. And what we have done to understand the sorption effects, the sorption enthalpy, as well as the sorption isotherms, we used the defined temperature program. So we desorbed the sample, then we cooled it down to a defined temperature, and then we switched on our water vapor generator at different levels of partial pressure water vapor. After the sorption has finished, we heat up again to a high temperature to desorb the material again, cool down to a different temperature level, and switch on the water vapor generator again. And this we have done for 3 different temperature levels. In this slide, you see now the results of the sorption measurement. So the blue colored points are the sorption isotherm, so the water uptake at different temperatures, at 43, 52, and 76 degrees centigrade. And you see, for example, for lower temperature, we have a higher uptake as for higher temperatures. The red colored points show the sorption enthalpy. And the sorption enthalpy, again, at lower temperatures is higher as compared to higher temperatures, which makes sense because if you have a higher uptake of the water vapor, you also should get a higher energy. And this we compared to current literature values, and we have seen that the methodology is valid that we use here. So STA can be used to understand the sorption isotherms as well as the absorption enthalpy of this zeolite material. Additionally, you also get the time-related behavior, because when you start the measurement, you see the uptake of the water vapor, so the adsorption over the time. And we have analyzed that for 3 different partial pressures, so for 6, 12, and 24 millibar of water vapor pressure. And you see here, for example, with a lower pressure, it takes much more time to reach an equilibrium state in comparison to a higher pressure. For example, here with the 24 millibar, we already reach an equilibrium in the system after 1 hour. So with the STA system, we can also manage to get the kinetic information of the material to understand how fast the adsorption or desorption takes place. Here another example how TGA and STA can be used for thermochemical materials to understand the reaction enthalpy. In that case, we measure the calcium oxalate monohydrate. You see that here it's a powder. And if you heat that up, you see in the first step, you're losing the hydrate, so the water molecule. In the second step, you start from the calcium oxalate and get the calcium carbonate. And finally, at higher temperatures, you get calcium oxide. And if you measure that in the TGA, you see the mass changes of every reaction step, and you also get the reaction enthalpies for every step. The third method I want to show you is the so-called laser or light flash system or apparatus, LFA. This system is used to determine the thermal diffusivity of a material. What you do here is you have a system which is shown as a schematic here. You have a laser with a laser beam shooting on the bottom side of your sample, the bottom surface. And with an IR detector, you look on the upper side of the sample. So when you are in isotherm conditions, let's assume we are at a constant temperature of the furnace, we apply a short heat pulse with the laser, which is absorbed by the sample. And then we measure with the IR detector the response of the so-called temperature curve. And now when we have normal experimental conditions, the curve looks like that. You have a half value time until you reach the maximum, and then it's cooling again the environment. So this is the experimental curve. And what we need to know is this half value time, the half value until we reach the maximum. And when you know this half value time, and if you know the thickness of your material, so shown here, this delta, then you can use Parker's law to calculate the thermal diffusivity. And as you can see here, these are the only 2 parameters I need to measure the thermal diffusivity. So there is no temperature in this equation. That means we don't need to know the actual temperature. We just need to have this qualitative curve to get this half value time. So in principle, we are talking about a time measurement and not a temperature measurement. This means we can measure the time much more accurate than temperature. So the thermal diffusivity, as long as the thickness is known pretty good, can be measured very accurately. Once this value is known, we can put this value, the thermal diffusivity, into this thermal conductivity equation, because when we then build the product from the thermal diffusivity, specific heat capacity, and the density, we get the thermal conductivity. This measurement can be applied on different materials, so we can measure on solids or compacted cylinder samples, on coated samples, but there are also special sample holders available, like liquid sample holders or powder sample holders. So let's have a look
on actual results of the laser flash technique. In that case, we analyzed a pouch cell. So you see a pouch battery cell like this here. We dissect this pouch cell into its components, the pouch, the anode, the cathode, and the separator material. On the right side, you see a diagram of the thermal diffusivity results of the pouch material. On the y-axis, you have the thermal diffusivity in square millimeters per second. On the x-axis, you see the temperature. And for the pouch itself, we measure the value around 25 square millimeters per second. This value represents the thermal diffusivity through plane of the sample. So we measure in that direction, but it's also possible to measure the thermal diffusivity in plane direction of your sample. This is possible with a special sample holder system. You see that here. So you have a sample holder with a mask which is collimating the beam, the laser beam, and another mask on the opposite phase to define an annulus of approximately 8 to 10 millimeters in diameter that is exposed to the IR detector. On this slide, you see some LFA results on the phase change material. In that case, we measured the paraffin wax with a transition temperature, melting temperature at around 70 degrees centigrade. So it's the same PCM as shown before in the results for the DSC. And we measured this PCM in a temperature range from room temperature up to 90 degrees centigrade. So we measure in the solid phase, so you see it here with these cylindric samples, but also in the liquid phase. And for the liquid phase, you see we have here a special sample holder system where we have this sample inside a polymeric ring and a steel support, so that it's also possible to measure the sample when it's melting inside this ring and that the liquid is not coming out of this ring or this steel support system. For the solid phase, it worked pretty fine. For the liquid phase, you see here strong deviations in the thermal diffusivity. And the reason for that is that we still have a kind of leaking of the sample out of the sample holder due to its low viscosity, but also the problem of air bubbles inside the sample. The last method I want to show you is the so-called heat flow meter method, or HFM. The HFM method is a steady state method to determine the thermal conductivity, and it's working with a defined temperature difference across the sample. You see that here. So you have a hot plate and a cold plate, and in between you have the sample. And when the temperature of the hot plate and the cold plate is constant, and you have a temperature difference between these two, you get a constant heat flow over a defined area, resulting in a heat flux density. And this heat flux density is the heat flow divided by the area, and this is equivalent to the thermal conductivity times the temperature gradient divided by the thickness. In that case, you always have to also calibrate the system with a well-known reference material. In our case, we use this fibrous glass board as a reference. So there we know the values very good. So below 1% of uncertainty with this calibration material. And then once this is calibrated, you have a calibration factor. This is this N factor you use for the calculation of the thermal conductivity of your sample in the end. It's a very good system to measure materials with low thermal conductivity. So below 2 watts per meter Kelvin is possible. Above that, you already get problems due to thermal resistances of the contact conditions from the hot plate to the sample or from the cold plate to the sample. So for samples with a higher thermal resistance, this system is working pretty good. If the sample has a low thermal resistance, you get high uncertainties due to the contact conditions of the hot plate and the cold plate to the sample. Here you see now an application of the heat flow meter on the measurement of pouch cells. So we measured here the effective thermal conductivity through plane of the pouch cell. In that case, you see we stacked here 5 pouch cells one after each other to increase the thermal resistance of the sample and to decrease the uncertainty in the measurement. Additionally, we placed 2 silicon mates on the bottom and on the top side to get better contact conditions between the plate and the sample itself, or the pouch cell itself. To get accurate temperature measurements, we additionally attached 2 thermocouples to the pouch cells on the upper and the lower side. So these are the results of the effective thermal conductivity measurement of the pouch cell in the heat flow meter. Here in this diagram, you see on the y-axis the thermal conductivity and on the x-axis the temperature. And we measured the stack in different variations 3 times. So we had 3 different runs at a state of charge of 50%. And what we see here that we get high reproducible measurement results over the whole temperature range. In that case, between 0.7 and 0.8 watt per meter Kelvin. The heat flow meter system can also be used to measure the specific heat capacity. We applied this method on the same setup as shown before on the pouch cells. So the methodology is you do a simultaneous temperature increase of both plates, of the upper and the lower plate, while the temperature difference between the 2 plates is minimal. And then you record the heat flux over the time and integrate it. So the heat which is absorbed by the sample at each temperature step is then calculated. So if you do that according to this methodology, you know the energy, you know the mass of your sample, and you know the temperature. So out of that, you can calculate the specific heat capacity, CP. And in this diagram, you see now the results for the pouch cells over the temperature from -10 to 50 degrees centigrade. And on the y-axis, you see again the specific heat capacity. The uncertainties are pretty high, especially at 0 degrees centigrade. So normal, we say we have an uncertainty of approximately 10% here in the specific heat capacity measurement, which is much higher than with DSC measurements. But especially here at 0 degrees centigrade, this high uncertainty comes from crystallization effects of water, which is in the system because the system is not completely inert, so it's not evacuated. You have the environmental conditions as in the lab. So if you have a humid air in the lab and you cool down below 0 degrees centigrade, you can have crystallization effects of water which is inside the system. And that's the reason here for the big uncertainty at 0 degrees centigrade. So we are coming to the end of this lecture. So let's conclude on the points we discussed here. So the first point was about the DSC measurements. So DSC measurements can be used to measure the phase transition enthalpy as well as transition temperatures of phase change materials, depending on the applied measurement procedure. For TGA and the DSC setup, so STA or TGA setup, can be used to measure thermochemical materials, especially sorption loading, enthalpy, and reaction enthalpy, as well as the kinetics. The laser flash measurements have shown that it's an accurate possibility to determine the thermal diffusivity of battery components, as well as PCMs in the solid phase. And we could also show with the heat flow meter method, it's possible to do non-destructive measurements for specific heat capacity and effective thermal conductivity of lithium-ion cells. So finally, I hope you enjoyed the lecture. Thank you for your attention. If you want to get more information about this topic, or if you have additional questions, just contact me. You see my contact information here on this slide. So thank you very much and have a good day. Bye.